Tutorial 4: Aerodynamics of Flight. This training tutorial will discuss aerodynamics of flight. In order for a pilot to safely execute maneuvers in flight, it is important to understand the aerodynamic forces acting on an aircraft in flight. The four forces acting on an aircraft in straight and level, unaccelerated flight are thrust, drag, lift, and weight. Thrust is the forward force produced by the power plant, propeller, or rotor, and is opposed by drag. Drag is the rearward, retarding force caused by air that has been disrupted by the wings, rotor, fuselage, and other protruding objects, and opposes thrust. Weight is the combined load of the aircraft itself, the crew, the fuel, and the cargo or baggage. Weight pulls the aircraft downward because of the force of gravity and is opposed by lift. Lift opposes the downward force of weight. Lift is produced by air flowing over the airfoil and acts perpendicular to the flight path through the center of lift. In straight, level, and unaccelerated flight, the sum of the forces acting on the aircraft is zero. This is, for the most part, true during climb and descending flight, but things are a bit more complicated. Any time the flight path of the aircraft is not horizontal, lift, weight, thrust, and drag vectors must each be broken down into two components. For example, during a glide, part of the weight of the aircraft points forward and therefore acts as thrust, or as the picture shows, during a climb, the weight can oppose lift and also thrust. A pilot may hold an aircraft in straight and level flight at many different airspeeds. The pilot needs to coordinate the angle of attack with the speed of the aircraft. For example, if the plane is flying at a high rate of speed, the angle of attack can be relatively low. However, if the rate of speed is low, then the pilot must have a higher angle of attack. This is caused by the amount of lift produced by the wings of the aircraft. The higher the angle of attack, the more lift is provided from the wing. If a pilot can maintain a high angle of attack and a coordinated thrust level, the aircraft can fly straight and level at low speeds. Level flight at even slightly negative angle of attack is possible at very high speed. Certain aircraft have the ability to change their direction of thrust rather than change their angle of attack, such as the Harrier jump jet on the left and the Osprey on the right. These aircraft can point their thrust straight up without having to point their nose in that direction. The Harrier jet uses vents to accomplish this, and the Osprey can rotate its propellers to point up. This allows each aircraft to hover over the ground or fly straight and level very slowly. Drag is the force that resists movement of an aircraft through the air. There are two basic types: parasitic drag and induced drag. The first is called parasite because it in no way functions to aid flight, while the second, induced drag, is a result of an airfoil developing lift. Parasite drag is any drag that is not caused directly from the aircraft producing lift. It is broken down into three categories: form drag, interference drag, and skin friction. Form drag is a drag that is caused by things like the cowling, antennas, and the aerodynamic shape of other components. How quickly airflow rejoins itself is determined by the shape of the object it's flowing around. As the picture on the left shows, the best way to reduce form drag is to streamline as many of the aircraft components as possible. Interference drag comes from the intersection of airstreams that creates eddy currents, turbulence, or restricts smooth airflow. For example, the picture on the right shows the intersection of the wing and the fuselage at the wing root. This area has significant interference drag. Air flowing around the fuselage collides with air flowing over the wing, merging into a current of air different from the two original currents. Skin friction drag comes from the surface of the aircraft not being completely smooth. Even though a surface may look smooth, it has a rough, ragged surface when viewed under a microscope. This non-smooth surface causes an interruption in airflow and more drag. Induced drag is the second basic type of drag. When an airfoil produces lift, there is always drag. This drag comes from wingtip vortexes. When the aircraft is viewed from the tail, these vortices circulate counterclockwise about the right tip and clockwise about the left tip. Bearing in mind the direction of rotation of these vortices, it can be seen that they induce an upward flow of air beyond the tip and a downwash flow behind the wing's trailing edge. This induced downwash has nothing in common with the downwash that is necessary to produce lift. It is, in fact, the source of induced drag. This downwash over the top of the airfoil at the tip has the same effect as bending the lift vector rearward. Therefore, the lift is slightly aft of perpendicular to the relative wind, creating a rearward lift component. This is induced drag. Drag is the price paid to obtain lift. The lift-to-drag ratio is the amount of lift generated by a wing or airfoil compared to its drag. This also governs the airfoil's efficiency. Aircraft with higher lift-drag ratios are more efficient than those with lower lift-drag ratios. The lift-drag ratio is determined by dividing the lift component by the drag component, or above by dividing the lift equation by the drag equation. L is the lift force in pounds. CL is the lift coefficient. P is density expressed in slugs per cubic feet. V is velocity in feet per second. Q is dynamic pressure per square feet. And S is the wing area in square feet. On the graph to the left, the lift curve, red, reaches its maximum for this particular wing section at 20 degrees angle of attack, and then rapidly decreases. 15 degrees angle of attack is therefore the stalling angle. The drag curve, yellow, increases very rapidly from 14 degrees angle of attack and completely overcomes the lift curve at 21 degrees angle of attack. The lift-drag ratio, green, reaches its maximum at 6 degrees angle of attack, meaning that at this angle, the most lift is obtained for the least amount of drag. Any angle of attack the aircraft operates at other than the lift-drag max point will cause more drag. Therefore, for the least amount of drag to lift, the aircraft must fly with that angle of attack. Gravity is the pulling force that tends to draw all bodies to the center of the Earth. The center of gravity may be considered as a point at which all the weight of the aircraft is concentrated. If the aircraft were supported at its exact center of gravity, it would balance in any attitude. This weight force acts downward through the airplane's center of gravity. In stabilized level flight, where the lift force is equal to the weight force, the aircraft is in a state of equilibrium and neither gains nor loses altitude. If lift becomes less than weight, the aircraft loses altitude. When lift is greater than weight, the aircraft gains altitude. The pilot is able to control lift. If the control yoke is pushed forward or pulled back, the angle of attack changes and therefore the amount of lift changes as well. For an aircraft to continue to produce lift, the aircraft airfoil must be continually attacking new air. On helicopters, this is accomplished by the rotating blades. In a fixed-wing airplane, this is accomplished by the airflow over the wing. The lift provided from the wing is proportional to the square of the aircraft's velocity. Lift and drag also vary directly with the density of the air. Density is affected by several factors: pressure, temperature, and humidity. At an altitude of 18,000 feet, the density of the air has 1/2 the density of air at sea level. In order to maintain its lift at a higher altitude, an aircraft must fly at a greater true airspeed for any given angle of attack. Warm air is less dense than cool air, and moist air is less dense than dry air. Lift varies directly with the wing area. If the wings have the same proportion and airfoil sections, a wing with an area of 200 square feet lifts twice as much at the same angle of attack as a wing with an area of 100 square feet. For most situations, the pilot controls lift and velocity to maneuver an aircraft. As stated previously, wingtip vortices are caused when the high pressure below the wing attempts to rejoin the low pressure air around the wingtip, causing a downward and outward vortex. The above picture is a more detailed diagram of how this process looks on a wing. The heavier and slower the aircraft, the greater the angle of attack and the stronger the wingtip vortices. Wingtip vortices lead to a potentially hazardous condition called wake turbulence. To avoid wake turbulence, avoid flying through another aircraft's flight path. Rotate prior to the point at which the preceding aircraft rotated when taking off behind another aircraft. Avoid following another aircraft on a similar flight path at an altitude within 1,000 feet, and approach the runway above a preceding aircraft's path when landing behind another aircraft. And finally, touch down after the point at which the other aircraft's wheels contacted the runway. A hovering helicopter generates a downwash from its main rotors similar to the vortices of an airplane. Pilots of small aircraft should avoid a hovering helicopter by at least 3 rotor disc diameters to avoid the effects of this downwash. Wind is also an important consideration when dealing with wake turbulence, because it can push around wake turbulence. For example, if there's a 10-knot wind, it will push the wake turbulence in the direction of the wind at a rate of 1,000 feet per minute. If this is a problem, pilots may also wait approximately 3 minutes for the wake to dissipate. Ground effect is a phenomenon that allows an aircraft to fly slower than normal a few feet from the ground. When an aircraft in flight comes within several feet of the surface, ground, or water, a change occurs in the 3-dimensional flow pattern around the aircraft because the vertical component of the airflow around the wing is restricted by the surface. This alters the aerodynamics of the wing mainly. The fuselage and tail surfaces are also affected, but ground effect mainly consists of the aerodynamic characteristic changes of the wing. The reduction of the wingtip vortices due to ground effect alters the lift distribution of the wing and reduces the induced angle of attack and induced drag. Therefore, the wing will require a lower angle of attack in ground effect to produce the same lift. The reduction of induced drag due to ground effect means that less power is required to fly at a certain speed. Most of the time, ground effect will produce a higher pressure at the static source, and the indicated airspeed will be lower than normally required. When an aircraft is taking off, the reverse happens from landing. The aircraft taking off will require an increase in angle of attack to maintain the same lift, experience an increase in induced drag and thrust required, experience a decrease in stability and a nose-up change in moment, and experience a reduction in static source pressure and increase in indicated airspeed. This is something to consider on takeoff because it could mean a pilot attempting to take off will feel like the aircraft can lift off the ground prior to the recommended takeoff speed. As shown above, this could cause the plane to have poor initial climb performance and also, in extreme cases, prevent the aircraft from becoming airborne entirely. Axes of an aircraft will be covered more in depth in the Flight Controls chapter. Please help us spread the word about Pilot Training System and we look forward to further servicing your flight training needs.